Okay, for this module, it's advanced themes for visualization. So I'm gonna introduce a number of more advanced themes related to visualizing your data and perfecting your plots towards publication quality figures. So we're going to use that fish community data set that we have been using, which again is the long-term resource monitoring element of the Upper Mississippi River Restoration Program's community data. So this is a subset of data from 2018 of just a subset of that fish community. So to begin, let's load the tidyverse and lubridate packages as well as the fish data set, and we can look at those fish. So this is a smaller data set than what we have been working with, just to make it a little bit more manageable. But we got 8 columns and 4,809 individuals here. The first thing we're going to talk about is faceting. So faceting is basically making multiple figures of the same thing, but it varies by some sort of factor like species or habitat, or here we're going to do species and field station. So it's automatically telling ggplot to make separate figures of the data based on one of these factors. You do not have to make multiple different plots. You don't have to do anything like that. Specifically, that's going to take a lot more time. Just facet. There are 2 different ways to facet, which we are going to facet by species and field station, but differently using these ways. And the 2 functions are facet wrap and facet grid. Facet wrap first makes individual plots grouped by some sort of variable or variables. What it's doing is changing a 1-day sequence of panels into 2 dimensions. And it's wrapping it so it's a lot neater, while facet wrap takes rows or facet grid, sorry, takes rows and columns to facet by. This way it's taking like one and just making it a little bit neater than facet grid, but they're pretty much interchangeable. So what we're going to do here is make a bar chart of different species and the fish count for species by field station. So this is what we've been doing in other modules. We're taking ggplot, specifying our data set, and because it's a bar chart, we only have one variable here that's a factor, and that's species. So ggplot species, specify our geometry is our position is dodged, so we're going to have side-by-side bars, and our color is black, so the outline of the bars will be black. We'll see what that looks like. So we got our species, our gray default bars with an outline in black, and our count, because stat count is associated with geom bar. Automatically creates that sample size. What we also want to do is know if the number of species changes by field station or collection site. So we're adding facet wrap. This tilde is what we're facet wrapping by, is field station, that F station value. And what you can do is save a bunch of plots, just like objects. Just like anything else, our data we've been doing, you just name it, the arrow, and you save it. So we saved it as this P0A, and we can call that object to see what our figure looks like. So we have all the different species on that x-axis, we have the counts on the y-axis, and it's faceted by the 6 different field stations. So now we could compare those field stations and see that, hey, field station 6 has the most channel catfish caught, for example. It's the highest bar. I will note that the default, and what I always see with these facet plots, is that the y and x axis are the same scale for every single one of these plots, which does make them comparable across your groups. Facet grid here splits plots by a grouping variable for the rows, which is your first value you specify, and the columns, which is the second value. It doesn't necessarily wrap your data nicely. We've got 3 plots in 2 rows in facet wrap. It may or may not do that in facet grid depending on the number of factors you have. For this, we're making a different type of plot. We're using our fish data set. We are using aesthetics of the sampling date and the temperature. So we want to look at how temperature changes across the sampling date using a scatter plot. So what this is going to look like is we have our S date or sampling date on the bottom, which you can't read those labels because the dates are really long. And then, so they all kind of just bleed together. And the temperature on the y-axis, and all the points are temperature by sampling date. But we want to look to see maybe this changes by species for some reason. We could just do it as a factor just to show you can do it multiple ways. But it probably changes by field station because they have different longitude latitudes. So we use facet grid. We say field station for our rows, tilde, so by species for our columns. What this looks like then is we have our field station as rows. So the first row is field station 1, which is marked on the very right, 2 for the second row, 3, and so forth. And then across the top in our columns, we have our different species. So bullhead minnow, bluegill, channel catfish, etc. So we can compare temperatures for each of these species and field station. It probably by species doesn't make a lot of sense to facet this, but this is just for illustration. But for faceting by field station, that makes a lot of sense since they are different longitudes and latitudes. We could look at how the different field stations differ in temperature across the season, for example. We could change this to facet wrap. And it's going to do the same thing, but instead of having like the rows and columns separate, so for facet grid, we had this what's called the strip. The strip on the right is our strip text, the strip on the top is our strip text, and it's either species or field station. With facet wrap, it doesn't have those two forms of strip text. It just has one, and that's at the top. So it's field station 1, bullhead minnow, bluegill 1, or field station 1, bluegill, so forth. And it makes the figure really tiny in this viewer. Once you save this plot to a large enough size, it won't look like this. It'll look actually fine, but it's just really smushed in the viewer. That's the nuance between facet wrap and facet grid, is grid's going to have the row by column designation, and facet wrap is pretty much just wrapping into a more neater pile. So it depends on what you are interested in or which faceting function you use. But going back to the temperature data, looking at it, we doubt it varies by species or that that's important because they're from the same field station. So we're just going to look at the patterns among those field stations. And it's sometimes easier to interpret patterns if the field station is a column instead of a row. This period indicates that we have no row grouping variable. And we can see what these do. So ggplot this, same exact thing we have been doing. Ggplot data, S state and temperature, and our G on point to get our scatter plot. And then we're going to add this facet grid with this period and say by column for field station we want to compare this. So we have columns of field station here, 1 through 6. And we can probably interpret these data a bit better because we see temperature increasing or decreasing on that y-axis across time and compare differences there. If we put field station on the other side, and then we put a period here, and it's just by rows then instead, which is not as comparable if we wanted to compare temperature specifically because they are not lining up on the same x-axis for all field stations. So that's why columns might be a little bit better to interpret because then we can say, oh, at these like middle dates, field station 1 has a lower temperature than field station 6, as an example. So that's faceting, which can be really helpful for making a lot of plots of the same thing repeatedly without just copying and pasting code constantly and trying to finagle these plots together into combination plots. But when we do have to make combination plots, it I've struggled with this a lot until I found a really good solution for that works for me. And it's relatively simple. It's just I couldn't figure it out at the beginning. So I want to provide this code for you. There's two packages that are really helpful for this, and it's cowplot as well as grid extra. So either can really be used. Here is some documentation of cowplot as well as grid extra to learn how to use them. Cowplot is pretty nice, so we'll use this one to illustrate the basics of combining plots. Depending on what you want to accomplish, you may use a combination of these two different packages, but note that there are more ways than what I'm showing here. So within cowplot, we can use the plot grid function to paste together figures. These need to be figures that have already been saved as an object, which is why we create these objects up here, P0B and P0A. The argument is generally figure 1 here, figure 2, etc. So if we load package cowplot, we plot our grid when we just put in our first figure and then our second figure. And they're pasted together. The default here is that the size of each plot is the same. So it might smush some of these plots. Or if you have like legends and stuff, it's going to like smush them a lot more. So that's something that can be changed pretty easily with code online. One of the nice things about saving these compilation plots or anything is that you can control the number of columns you have or the number of rows. So there's a lot you can do with these, and it's explained really well in that vignette or those two vignettes that are here on what you can actually include. So this one is going to be, there's no one column, so we're just having them in one single column instead of one row. There's a lot to do. So if we look at plot grid in the help, let's see if it gives us anything. You can align them to make sure that they're aligned. You can change axes. You can specify the number of rows and columns. The relative widths is really helpful. So if you have a really narrow figure and a wide figure, you can actually change the widths as well as the relative heights. So if we did like widths for these two plots, we can use concatenate and then like 1 and 2. We'll see what that does. I don't know if that did anything just because we have the columns there. So let's see. There. If you're not having it in the same column, but you're having it in the same row, relative widths is super helpful because it makes this first plot have a relative width of 1. This second plot have a relative width of 2, so it's double the width of it. If we wanted to do it with the end call as 1, we just change that to relative or rel heights. And it would be the same thing where the first one is smushed more and the second one's like double the height of that. So that's a way to play around with it. You can add labels and change the labels, which I always find helpful. Labels equals concatenate A, B, and it'll label these as figure A and figure B. You can do a lot in here. There's so many different arguments. Play around with this to see what information you need and what you have to put in here to make a really good compilation figure, if that's your goal. Next, we're going to talk about reordering factors. So now we know how to make compilation plots and how to facet them. But sometimes we need to reorder factors in our data because ggplot automatically plots everything based on alphanumerical order. However, alphanumerical order does not always make sense. So, like dates or characters, it's going to plot October before July because 110 comes before 7 in that month sequence. So, to combat these issues of alphanumerical order, you can use a factor reorder to plot based on logical sense. So if we go in our fish data set, and this is showing also that we can pipe directly into ggplot from our dplyr information. So if we pipe from our fish data set and we say, let's mutate our species column to be in a more logical order than what its default is. So we say species equals factor re-level is the function. This is just like using factor recode or factor collapse. It's just called factor relevel, and we're just reordering those factors. We need our species to be as a factor, so we can change that there if we want to coerce it. But let's say we want them to like increase in trophic position from like a detritivore herbivore to more of an omnivore or predator, rather than having it alphanumerically. So emerald shiners an herbivore, gizzard shads an herbivore, bullhead minnows an herbivore slash omnivore. Bluegill is more of an omnivore. Freshwater drum is getting more benthivore predator, and channel catfish is like an omnivore too. So that's the sequence we want in here. For example, something that's more logical. And then the rest is just what we have been doing. We're making bar charts that are filled by field station, vary by species. It's counting them for our sample size. We're just rearranging the order of those bars. Because we piped from the fish data set, we don't have to specify the fish data set here because it knows from the pipe that it's going into this ggplot. So we pipe from the fish data set, we mutate it, pipe again, and then we start a ggplot sequence. And note that within ggplot, you must use the plus signs and not the pipe. Oh, got angry at something. Let's go back to that. Okay. So we have our species that are now reordered. They're not alphanumeric anymore. They are a new sequence that makes sense logically by some sort of scenario, like trophic guild for this, and our counts and our factors of field station. So we can reorder those factors pretty easily. That's just something I find that really helps readers make sense of the data, since most things aren't alphanumerical order and logically wise, at least for factors. All right, we're going to talk about some advanced ggplot tweaks. So we're going to continue this idea of themes that we started in the basic themes, altering our themes so we can have more publication quality figures, things that make more sense with our data, adding scales, removing this ugly like gap between 0 and the x-axis, etc. And we're going to be saving our plots as objects and then just adding on to them as a way to show that, yes, you can save your plots and then add on to them later. So we're going to make a base plot first, which is the plot we just made. Specified our data set and piped, and then we mutated species as a factor here and field station as a factor. And then we are saying we're going to plot and switch to that plus sign. We're filling by field station, and on the x-axis is species, the position is dodge, and color is black, so the outline. So our base plot is essentially what we just made, but we aren't factor releveling for this. We aren't, we're just using the alphanumeric factors here, which is fine. So this is our basic plot. Now we're going to adjust the labels how we want them. I want to note that you can update the plot from above by just adding to the object. This is no different than just adding another line of code to the code chunk above. We saved it as object P1. We're going to go from there. P1, And then you say plus because we're in ggplot. So from this plot, add a y-axis label that is count, uppercase, an x-axis label that is species, uppercase, and a title of fish collections across field stations, plus this labs function, sorry, allows us to change what's in the legend. And because we filled by field station within this function, fill here by field station, we're saying our labs for fill equals field station. We want it to be field station, not F station, because F station doesn't make sense for anyone else not looking at this. So we added that, and we can see what we did. We added a title, we changed the X and Y axis labels, or axis titles, and then we added that field station for the legend. Now, a lot of these colors are, it's the default colors. They're not very good. They kind of, looks tacky. Maybe we want to add our own colors. So we're going to add onto the object we just saved, which is that plot. And we're going to say, okay, plus, let's do a scale fill manual. Fill because the bars are filled and we specified fill. And we want these colors, so our values equal concatenate, and these hexadecimals in sequence. If you don't understand this line of code, please refer to the color module before this. But now we have our nicer colors. They're not as tacky, they go well together, they're not super clashing. Great. Let's keep building on this. We're going to use this scale y continuous to change the y-axis scale limits from 0 to 400 instead of just ending at 300 when our bars keep going up. And we're going to make the tick marks starting at 0 and ending at 400, and a new tick mark and number every 50 instead of just every 100. So we add the scale y continuous. It's the same exact thing for scale x continuous if you had these values on the x-axis instead. Our limits are how far this y-axis goes. So we want it to go from 0 to 400, for example. And our breaks are where those tick marks are. So we want them at 0, we want them at 400 to go from 0 to 400, and we want them every 50 units. So if we save this, we now have it at 0 to 400, and it goes every 50 units. And then finally, we're going to update some of those attributes of the figure using the themes. Here, we started with some themes in the basic themes module, but here we're going to add a lot more, and some familiar ones as well. So we're going to change the panel background to element blank. Right now it is because I have the global themes view on my R profile right now. But if it's not already, if it's still like the gray gridded on yours, you can change it this way. We're going to alter the axis, the x-axis title to be a larger size and boldface. Same with the y-axis title. We're going to alter the plot title to be larger size and boldface and to horizontally adjust it to the middle of the figure. And we're going to change the axis text to size 10, so increase size, and color is black instead of the default gray. All of this stuff is from the original basic themes. This is all, we did that there. All of that should be familiar. This is some of the new stuff. We want to change the x-axis text to be at an angle of 45 degrees. Sometimes when your axis labels are smushed together, angling them can be really helpful. Here, it doesn't make a lot of sense to angle them, but we're going to do it for just purposes of showing how to do it. We're only doing this for the x-axis text. That's why it's axis.text.x. Element text angle equals 45. So they should be at a 45-degree angle. We're going to alter the legend text. So the text within the legend we want that text size to be 8. We can change the color, we can change whatever we want here. But we're just altering the text size right now. We want the legend title to be larger as well. So we're making that size 12. So the text itself will be 8. The size will be 12 for the title. And then we can change the legend position too. We can make it right, which it already is. We can make it left. So let's make it left and see what happens. What does this do? It shifts the legend to the left, like we said. It angled that x-axis text, which is pretty ugly right now. It bleeds into that figure. But we have a nice large, bold title, large, bold X and Y-axis labels, black X-axis and Y-axis text, good labeling around here, and a nice legend. So we can have that legend on the left. We can use the default right, wherever you wanted to put that. We're going to do it on the right moving forward. So now that we've saved this as another object, we're going to keep adding to this. Let's say we want to alter the labels of our legend because 1 through 6 does not make any sense. We could alter this before making the plot using a factor recode in dplyr, but we can also do it within ggplot under scale fill manual where we have labels and we can make these labels then correspond to the color values. So label 1, color value 1 here. We want to make that pool 4. That's the sampling reach. The second one, pool 8, and that's this color value of the green. Pool 2 is 8, then pool 13, and so forth. So we're just going to relabel those labels there. Instead of 1, 2, 3, 4, 5, 6, they're going to be the sampling reach names. And these are just our colors that we had selected. And then we can further say within the themes argument, make there be an X or an axis line. We want an axis line there. So let's see what this does. That didn't add anything because we didn't do one other thing. But we have the field station labels here. Now we have the pools instead of 1 through 6. That makes a lot more sense to someone else looking at this figure. We'll notice this is one of my biggest things to change is this disgusting gap in between the x-axis and the 0. So the origin and the x-axis line, as well as the text running into that x-axis line. So within that scale y continuous function, which we could alter previously, this is the code we had previously. We could have put this extra part in that code as well. That is okay. But we add this expand equals concatenate 0, 0 to get rid of this gross gap. And here, when we do this, and we just run this, we now have that gap gone, which is great. That's what we wanted, is that gap gone. Let's see what this axis line does. I don't know why that keeps popping up here. I don't think that's really doing anything, but that's okay. What we can do to remove that text angling, or we can adjust it, is we could say axis.text.x equals element text, and we can horizontally or vertically adjust this text. Let's see what vjust1 does. That might be the default. There, if we v-adjust it by 0.5, so this is a vertical adjustment of the text, that text is no longer running into that x-axis line. It is further down, and it's much easier to see. And this is how you can alter the space vertically. If you did it horizontally, it's just h-just, like we did for the title. That's how you can remove that, it running into that x-axis line with the vertical or horizontal adjustment here. So for this figure, it's pretty well put together now. We probably wouldn't have angled text for the x-axis text here. We just leave it as the default horizontal, which is fine. This is just for show, but it's a pretty good figure right now as is. So this next part doesn't make sense to do with this figure, but because many people use superscripts and subscripts in their axis labels, I wanted to show that how to do that specifically. So here's how to add expressions or superscripts and subscripts. So these expressions tell ggplot that you're about to give it like some sort of math equation or something. What paste does is it pastes strings together of text or math that's separated by commas. The caret indicates a superscript. Brackets indicate a subscript. So we'll see what this looks like. This is kind of weird nuances when it seems like it should be easier, but it's not. If we wanted to alter the X and Y labels to have superscripts and subscripts, what we could do is say, all right, expression. We're giving R some math for this. We're saying paste. We want just this text, count of fish. So that's in quotation marks. And then comma, because we want to paste something else. It's cite superscript -1. So anything coming after that superscript is going to be, or anything coming after that caret is the superscript. And then that's also in quotation marks there. Or sorry, that's not in quotation marks. Quotation marks around text only. The expression doesn't need it. And then this has quotation marks for this parenthesis. So we're going to see what this looks like. Is we have count of fish cite -1, which means per cite. So that's just how to do a superscript. Anything that comes after the caret before the comma will be a superscript. The X lab, we want to do an expression, and we want to paste. Species is, this phosphate has nothing to do with this figure, but as an example of using chemical formulas in here, I'm going to say phosphate equals, and that's within quotation marks because that's just text. And our expression, our mathy bit, is then PO for phosphorus and oxygen. Within brackets are our subscripts, and then followed by a superscript of -3. We'll see what that looks like together. Is we have phosphate equals PO4 as our subscript because that was in the bracket, and then the caret followed by the -3 here as our phosphate equation. And we also have count fish per cite. Obviously, that phosphate axis does not make sense, but that is how you incorporate both superscripts and subscripts. There's a lot more you can do. You can add things like pi, delta, other Greek variables there within these expressions as well. Don't have that code here, but just to make this familiar to folks looking at it, this is how you add some expressions like superscripts, subscripts. And then finally, I want to talk about saving plots. We're inevitably going to need to save the plots to share with collaborators, to upload into manuscripts. And I recommend saving plots as a TIFF instead of a PDF or PNG because it generally results in higher quality figure that's transferable among software platforms. The issues with TIFF is that they take up a lot of space. They're like 8+ megabytes versus like a couple hundred kilobytes for like a PNG file instead. So I recommend TIFF, even though they're larger files, but they're based on vectors. So when you zoom in, they don't get grainy like they do with a PNG or something. We can also use this function to make PDFs, JPEGs, PNGs, etc. And if you don't specify which plot that you just saved, like in an object format, ggsave is going to save the last plot displayed. So the function is ggsave, and we specify our plot name. We're going to save this not this one, but our original one we had made with the nicer figures and labels. We're going to save P1F, and then we are going to name it fish counts by station.tiff. This extension is what you are saving it as. It could be a PNG, could be .pdf, .jpeg, whatever you want for that. You can also specify your file path name here. So if it's like a different path name, like we're going under within this folder, go into the data folder and then go into the plots folder and save it there. You can specify whatever file path name you have here. Without that rest of that path, it's just going to save it where this file is saved. And then you can specify your width and height, the units of your width and height, as well as the dots per inch for like how high resolution this is. So we have our width, our height, centimeters, and our dots per inch for a higher resolution. And we save this, and it's going to save this plot. And we can pull this plot up. And it saved our plot. It's got that stuff running into the x-axis probably because we didn't actually save that in the plot, but it looks pretty good other than changing that bit. So that's how you alter things to be more publication quality. So we went through faceting, altering more advanced themes, including things like adding equations, removing gaps in the data, altering continuity in the axes, as well as saving these plots. So all of this information combined, at this point, if you've gone through all the modules, you should know how to begin with raw data, wrangle it into a format that's usable for the creation of tables and figures, and be able to create relatively good quality figures that are ready for publication using colors and shapes and all this other information. I want to state that this is just an introduction to the tidyverse functions, and there's a lot more to delve into, but that this should give you a foundation and knowledge of the language being used, as well as the different types of functions that can be used and how you want to move forward with them to develop more advanced features in plots or data wrangling. So this should really lay a strong foundation for you moving forward.